Hi everyone, so my name is Teja. So today I am going to present the assignment we got. So let's start. So here we can see the problem statement, which is suppose we are given two strings x and y of total length n over a constant sized alphabet. Then we have to show how to compute the longest common substring in a linear time, which is order of n time. So I am selecting the suffix tree method to solve this problem. So that's why I just put it in the heading. So as we can see the problem statement, now let's go to the next part, which is problem definition. It is actually the explanation of the problem statement. So here we are assuming the two string S, which has length m, and T, which has length n. So let's find the longest string which is the substring of both S and T. So the generalization form is the k common substring problem, given that the set of string is S equals to S1 up to Sk. So here S is the set of all the strings, and here the summation of n is the total number of strings, and here we can find the longest strings which occur as the substrings of for at least k strings. So now let's find what is longest common substring problem. So in computer science, the longest common substring problem is actually to find the longest string which is present in between like two or more strings. So the problem can have multiple solutions. So the main applications which we can see for longest common substring problem is data deduplication and plagiarism detection. So when we want to detect plagiarism between articles or contents or essays, we use this method because it tries to find the common part of the essay with the previously written content. So it is like a very famous example of the longest common substring problem. Next, we will see an example, which is suppose there are some strings which is AB, ABC, BA, BCA, and ABC, BA. So here we have to find the longest common substring. So here the longest common substring is ABC. It has the length of 3. So the ABC is the longest common substring, and except that there are some other common substrings which are A, AB, B, BA, BC, and C. So here we can use many algorithms for this problem. So the one is, which is the most famous one, the suffix tree, and another one is dynamic programming. So here one can find the lengths and starting position of the longest common substrings of S and T in order of n1 plus n2 time. So here I am assuming that S have n1 length and T have n2 length. So with the help of generalized suffix tree, a faster algorithm can be achieved. So if the size of the input alphabet is 2 to the power root over of log n1 plus n2, then the algorithm will run in order of n1 plus n2 and log sigma by root over of log n1 plus n2. So here you can understand that n1 plus n2 equals to n, and and it will take this amount of time, and it will take order of n1 plus n2 log sigma by log or n1 plus n2 amount of space. So n1 plus n2, this one is actually n. Okay, so so there is another method which is dynamic programming. but it will cost order of n1 into n2, so you can say it as order of n square. So it is why we are not taking this example, because suffix tree is more sufficient because it takes order of n, but for dynamic programming it takes order of n square. So that's why we will prefer suffix tree over dynamic programming. So for dynamic programming, it will take order of n1 up to nk amount of space and order of n1 into nk amount of time. So I have written the dynamic programming, the pseudocode of the dynamic programming, so you can see how. So you can see here there are two for loops, so it is common sense that it will take order of n square amount of time. And for the rest of the part, I am just taking the longest common substring here in the function, then initializing the array, and then initializing z as 0, and then I am just doing the loop and then returning the rate value, which is actually the substring. So this one is the dynamic programming. As it takes order of n square time, so we are not taking it. So for next, let's find what is suffix tree. So in computer science, a suffix tree, it is also called pat tree. In earlier time, it is also called pat tree. So it is actually position tree. So suffix tree is a compressed tree containing all the suffixes of the given text as their keys and positions in the text as their values. So suffix trees allow particularly first implementations of many important string operations. So here you can see one example. So here you can see we get the answer at the root. So for our problem, which is we have two string of length of total length of n. So when we will compute it and when we will get the suffix tree, we will get the answer at the root. So here the longest common string is banana, so it is at the root, and the other strings are na, na, a, all these things. These are found in other places. So suffix tree from the text banana, each substring is terminated with special character $. The 6 paths from the root to the leaves correspond to the 6 suffixes as $, $, $, $, $, $, $, and banana $. So here you can just do in this way, like $, $, $, $, and in this way. So the numbers in the leaves give the start position of the corresponding suffix trees. Suffix links, these are drawn dashed during the construction. These are the suffix links. The construction of such a tree for the strings S and T takes time and space linear. So it will take linear space and time. Once it is constructed, several operations can be performed quickly. As we can see, it will take linear amount of time. So we can do several operations and it will be done really quick. So for instance, locating a substring in S, locating a substring if it contains a number of, when we are locating a substring, even if we do some mistakes, still we are going to locate it very quickly. So here we can find some application of the suffix tree. So it is the number one application is string search. We can do it in order of n time. Then finding longest repeated substring, finding longest common substring, which we are using for our assignment, and then finding longest palindrome in a string, data compression to find repeated data, data clustering algorithm. We are using the concept of suffix tree in data clustering algorithm, in suffix tree clustering algorithm, in Burroughs Wheeler transform. All these algorithms we can, so this one also is one algorithm. Let me write it. So we can use the concept of suffix tree in all these algorithms, and also recently we can use it in bioinformatics application for searching the patterns of DNA or protein sequences. It is really a huge implementation because for bioinformatics the amount of informations are really huge. So we need this type of algorithms to search for a pattern or protein sequence really quick. So it is really efficient for this kind of application also. So parallel construction. So here by parallel construction I mean that there are many algorithms to implement the suffix tree. So some will take the time of order of n, but recently it is more improved, and recently it is taking time order of log square in span. So we can say that the algorithm achieves good parallel scalability on shared memory multi-core machine, and it can index the human genome approximately 3 GB data. So we can use the concept right now to analysis the human genome, and it will like index approximately 3 GB, that huge amount of data, in under 3 minutes using 40 core machine. So it's a really big thing. So here now we are only discussing about the linear time, so we will not check about order of log square n time. So for order of n, let's see how to implement the suffix tree. So a suffix tree is a compressed trie of all the suffixes of a given string we will discuss about. So here the main key points are compressed trie, suffix tree construction using the concept of brute force, and Conant's algorithm. So suppose there are some strings like banana, NABD, BCDEF, BCFEG, and AAAD. So for compressed trie, we will get this kind of diagram. You can see here the diagram. So this one we will get for compressed trie. So we can say from it that as it has almost n leaves, n is the number of the strings inserted in the compressed trie, then the space complexity will be order of n rather than order of n square of a normal trie. So if we implement normal trie, then there will be 2 branches for each of them, and it will take the space of order of n square. So but for compressed trie it will take order of n. So for huge data analysis it's a really big thing because the space is less for compressed trie. So here we got why we are using compressed trie for suffix tree. Then as suffix tree is compressed trie of all suffixes of a given string, so brute force, we should consider the approach of brute force. But for brute force, the time complexity will be order of n square. So that's why we cannot use it. So because we need something which will give us the time of order of n. So if there is like large value of n, then the order of n square will be a problematic thing. So that's why we are not considering brute force. Then so we are right now we will consider about Conant's algorithm. So let's see what is linear time construction of suffix tree. So for linear time construction of suffix tree, so basically there are 2 methods for it. The first one is Conant's method and the second one is Weiner's method. But we will prefer Conant's method over Weiner's method because it is easier to understand and also it is faster to analysis. Though Weiner gave the approach for the first time, but we will prefer Conant's for these points. So now let's discuss about it. So for Conant's method, we will use the concept of implicit suffix trees. So this algorithm constructs a sequence of implicit suffix trees, the last of which is converted to a true suffix tree of the string s. So first we will use some general suffix tree, then we will convert it into implicit suffix tree. Okay, so let's see what is the definition of implicit suffix tree. So an implicit suffix tree for string s is a tree obtained from the suffix tree for s dollar. So here I am considering the string is s by removing every copy of the terminal symbol dollar from the edge labels of the tree, then removing any edge that has no label, and then removing any node that doesn't have at least two children. So here let's see about the suffix tree. So here we can, according to our definition, so here it will first remove every copy of the terminal symbol dollar. So first it will remove all the terminal symbols of dollar. Then it will remove any edge that has no label. Then it will remove any edge that has no label. And after that, it will remove any node that doesn't have at least two children. So like for this node, this doesn't have any, like no two children. So we are going to eliminate this. So an implicit suffix tree for a prefix s, here s is the set of the strings. Suppose it is from I to j of s. It is similarly defined by taking the suffix tree for s which is 1 to I dollar and deleting dollar symbols, edges, nodes. As above definition, we denote the implicit suffix tree of the string s 1 to I by I from 1 to m. So that means suppose s is the set of all those strings, and for all the nodes s has the dollar sign. So first we will remove the dollar sign, and then we will remove the edge which has no label, and then we will remove the other nodes which doesn't have two children. So in this way, lastly we will get the set of the string. So we will just operate on that. So the implicit suffix tree for any string s will have fewer leaves than the suffix tree. As we are removing all those things, that's why the implicit suffix tree will have fewer nodes. And for string s dollar, if and only if at least one of the suffixes of s is a prefix of another suffix. So here we suppose there is a string xa bxa. So for general suffix tree it will look like this, and there is the dollar at the end of the string. But for implicit suffix tree it will look like this. So it is much more lesser from, like it has much more lesser nodes and all those things. So here this is the main concept of implicit suffix tree, and for Euconnen's algorithm we will use this suffix tree. So first let's see Euconnen's algorithm at a high level. So it constructs an implicit suffix tree I for each prefix s of the string s, tiling from I1 and incrementing I by 1 unit until IM is built. The true suffix tree for string is constructed from IN, and the time will be order of n. First we will explain it by presenting a order of n cube method and then optimize it to order of n. Okay, so this one is the Euconnen's algorithm at high level. So here is the algorithm. So first we will construct a tree, and then we will just traverse it from I, like it will start from I1 to m-1. Then we will start it, so here we will increment the value of I by 1, and then we will do the loop, which is j. It will start from 1 to I plus 1. So here the extension rules will be applied. So what we have to do, we have to find the edge of the path from the root labeled as j2i in the current tree. If needed, extend the path by adding character is I plus 1, thus assuring that string is ji plus 1 is in the tree end. So here we will just find the path from root to the current tree, and then if needed we will extend the path by adding this character. So here in this way we just get the string, this one. So there are some rules for suffix extension. So let's see. So here as j2i equals to beta, this be a suffix of s I 1 to I. So suffix means which will comes later. So this will come like previous, and it will come later. So in extension j, when the algorithm finds the end of beta in the current tree, it extends beta to be sure that the suffix beta s I plus 1 is in the tree. So it will just extend b to make sure that this one is also in the tree, as it comes later, so it has to extend. So it has 3 rules for this. So the first is, in the current tree path beta ends at a leaf, that is the path from the root labeled beta extends to the end of some leaf edge. To update the tree, character s I plus 1 is added to the end of the label on that leaf edge. So to analyze the current path b, as b will end at a leaf, we will just look for the path from root to that leaf, and if needed we will extend it to some leaf edge, and then we will just end and we will just add this character at the end of the label of the leaf edge. So the second rule is, no path from the end of string beta starts with character as I plus 1, but at least one labeled path continues from the end of beta. So in this case, a new leaf edge starting from the end beta must be created and labeled with character s of I plus 1. A new node will also have to create it if beta ends inside the edge. The leaf at the end of the new leaf edge is given the number I. So the third rule is, some path from the end of string beta starts with character s of I plus 1. In this case, the string beta s of I plus 1 is already in the current tree as we are extending. So remembering that in an implicit suffix tree, the end of a suffix need not be explicitly marked, we do nothing. So as we remember that for suffix tree there should be a $sign, but for implicit we are removing it. So at the end of the tree we don't need any special mark, so we are doing nothing here. So next we will find about suffix lengths. So let's see what is suffix lengths. So how to implement it and how to speed up our algorithm. So let's x alpha denote an arbitrary string where x denotes a single character and alpha denotes a substring for an internal node v with path level x alpha. So if there is another node s of v with path level alpha, then at a point from v to s of v we'll call it a suffix link. So between those links, there, if it is connected, it will be called suffix link in simpler way. So to do that, we will use single extension algorithm. So let's find what is that. So it is first we will begin and then find the first node V at or above the end of the S. We know S is J to I, and then either it has a suffix links from it or it is the root. So first we have to check whether it is the suffix link or it is the root. Then it requires walking up at most one edge from the end of the S J to I in the current tree. Let Y denote S J to I in the current tree. Oh, sorry, one second. Let's Y denote the string between V and the end of the S of J to I. So Y will denote the string between V and the end, and we have to check whether it is root or link, suffix link, and then we have to walk through it. So if V is not the root, traverse the suffix link from V to node SV, then walk down from the SV for the following path of string like gamma. If gamma is the root, then follow the path for A sub J to I from root. Now for the third case, using extension rules, ensure that the string S of J to I, S of I plus 1 is in the tree. So we have already discussed about the extension rules. So here we have to make sure that S of I plus 1 must stay in the tree. So that's why we have to extend it if needed. So for the fourth step, if a new internal node W was created in extension J minus 1, string alpha must end at node SW. So it will create the suffix link from W to SW end. So this is the single extension algorithm. So the main thing is we have to like traverse from root and we have to cover all the suffix links. We have to make sure that S J to I should be in the tree. Now to improve it, we can implement 3 tricks. So let's find about the tricks. So for trick 1, suppose G is the length of gamma, G dash is the number of character, and S of V is the number of edges, and H is variable. So here if G dash is less than G, then algorithm doesn't need to look at any more of the characters on the edge. It simply goes at the end of the edge. Or if it equals to G, then it skips to the node at the end of the edge, sets G to G minus G dash and H to H plus H dash, and it will just choose the first character of H of gamma. Or if G is less than G dash, then it directly goes to the character of G, ensuring that the gamma path from SV ends on that edge, exactly G character down from its level. So there are 3 cases when G dash is less than G, when G is equals to G dash, and when G is less than G dash. So for this we can just see. So for the first one, it will simply go at the end. For when it is equals, it will just extend it G from G to it will be G minus G dash, and H will be H plus H dash, and then it will select the first character of H. And if it is less, then it will just select the exact G character down from its level. So this one is our trick 1. We are using these tricks to improve our algorithm. So next is trick 2. So for trick 2, end any phrase I plus 1 for the first time that extension rule 3 applies. If this happens in extension, then there is no need to explicitly find the end of any string. The extension is phase I plus 1 that are done after the first execution of rule 3, and it is said that it has to be done implicitly. So this is in contrast to any extension J where the end of SJ to I is explicitly found. An extension of that kind of is called explicit extension. So here we have to apply the rule 3 of the extension. So here we are applying this rule 3. You can see here this one. So and we have to see if we need to find the end of any string or not. So yeah, that's the thing. So then we'll go to the trick 3. So here in phase I+1, when a leaf edge is first created and would normally be labeled with substring S, instead of writing the indices of the edge, write PE, where E is a symbol denoting the current end symbol. E is a global index that is set to I+1, and once in each phase, the algorithm knows that the rule 1 will apply in extension I through J. At least it need to know additional explicit work to implement those J extensions. So here it will first in phase I+1, when a leaf edge is first created, it will normally be labeled, and we will just use one global index here. And then in phase I+1, since the algorithm already knows the rule, so there we don't have to use any more extensions. So instead it only does constant work to increment the variable E, and then the explicit work will start with the extension J plus I. So for all these tricks, we are just using this algorithm, which is single phase algorithm. So here we will first begin and then increment the suffix E to I plus I. Then explicitly we will compute successive extensions starting at J plus 1 until J star, where we will apply the rule 3, and then we will set J of I plus 1 to J star minus 1 to prepare for the next phase end. So we are using the tricks here in this algorithm. So lastly, creating the true suffix tree. So the final implicit suffix tree in can be converted to a true suffix tree in order of n time. First, add a string terminal symbol $ to the end of the S and apply the algorithm. Replace each index E on every leaf edge with number, and this can be done in order of n time. So after using implicit tree, we will again convert it into a suffix tree. So we have to add the terminal symbol $, and then again we have to remove the index from the leaf edges. So it can be done in order of n time. So here in this way you can prove that the Euconnen's algorithm builds a true suffix tree for S along with all its suffix links in order of n time. So as I have previously said that for our problem we can find the longest common substring at the root of the suffix tree, and it can be done in order of n time. So first, when we will get the problem, we will construct a suffix tree. We will then convert it into implicit suffix tree, and then after doing all those things in order of n time, we will again convert it into a true suffix tree, and this can be done in order of n time. So this is my presentation for the assignment. So thank you for watching.